This is a sine wave. A sine wave is the basic building block of sound. Any sound can be constructed by combining several sine waves in different frequencies. The sine wave gets its name from the sinusoid function, which describes a circle in 2 dimensions. Since sound only exists on 1 dimension, the time dimension, the graph cannot go back on itself to create a real circle. So basically, a sine wave is audio's circle. Just as you can create a complete drawing from small dots, you can also create any sound conceivable by mixing together several sine oscillators. Let's listen to the sine oscillator. The graph you are looking at is an oscilloscope. The y-axis represents the amplitude. This is the 0 point, this is the maximum, and this is the minimum. And the x-axis represents time. The y-axis acts exactly as your speaker would. When the graph is on top, your speaker is pushed forwards towards you. When it's down, the speaker is pulled away from you. When it's on 0, then your speaker's driver is centered on an ideal state. When I play high notes, more wave cycles are compressed into the view. This is because high frequencies are shorter and our graph has a set time window. If we play low notes, we can see that there are less cycles in our view. This is because they are slower and they take more time to evolve. Let's look at the sine in our frequency analyzer. As you can see, the sine only has 1 peak and has no frequency content on any side of the spectrum. This is why a sine wave is often referred as a pure tone, as it is the only sound that consists of a single basic frequency. This basic frequency is called the fundamental frequency. If we look at other wave shapes, such as the saw or square, now we're looking at a saw wave on an oscilloscope. If we look at the frequency analysis of the sound, we can see that it has many spikes. Those spikes are extra high frequencies that construct the sound's timbre. Those are called overtones. Overtones construct each sound that we hear each day. Overtones can be harmonic or non-harmonic. Non-harmonic overtones result in noise or sounds with ambiguous pitch, while harmonic overtones support the fundamental frequency and keep its tonality intact. So as you can already guess, we can make a saw oscillator out of many sine oscillators. The lowest frequency of the sound is the basics on which the sound is built and is called the fundamental frequency. The rest of the spikes here are called overtones. Harmonic overtones will always be the fundamental frequency multiplied by a whole number. Let's take for example the note A, 110 Hz. It has a fundamental frequency of 110 Hz, and its first harmonic is its fundamental frequency, 110 Hz. Its second harmonic would be the frequency times 2, which means 220 Hz. The third one will be 330 Hz, times 4, times 5, and so on. The idea behind the system is to keep our wave cycle repetitive, and the only way to do that is to have the overtones start and finish at the same phase of the fundamental frequency. As you can see here, we have a green, blue, we have small sine waves here that represent the harmonics of the sound. The first harmonic would be the fundamental frequency. The second harmonic has 2 cycles per 1 cycle of the fundamental frequency, and because of that it starts and it ends at the same point. And it's the same with the third harmonic, which has 3 cycles per 1, or here we have 4 cycles per 1, and you can actually follow it, it's pretty accurate. And so on to infinity. Let's listen to those harmonics. Does it sound musically familiar? Of course it does. This is the building block of all music. It occurs naturally in nature, and it exists in all human music. Personally, for me, it reminds an Indian flute or something like this. Let's see how a saw wave is constructed from many sine oscillators by adding them one by one. Let's start with the fundamental frequency, and now we add the second harmonic, third harmonic. As you can see, there are 3 slides here, and it's starting to resemble a saw shape. We are going to add this harmonic here. And I could go on forever, but my CPU doesn't have enough horsepower, and 16 is enough to demonstrate the idea. A saw wave has all of the harmonics, but not all waves have to have all of the harmonics. For instance, the square does not have any even harmonics. It skips the 2, 4, 6, 8, and so on of the harmonics, adding only the odd harmonics. So 1 is the odd harmonic. As you can see, 2, we're not mixing inside, we're skipping it, straight to 3. And voila, it starts to look like a square. We skip the 4th harmonic, 5th we add in, we skip the 6th, we add the 7th, and so on. Let's look at the same thing on the frequency analyzer. Here is a saw wave. This is our fundamental frequency, and now we're going to add the overtones. Let's look at our square wave. The first one, second one we skip, third, 5th, 7th, let's look at the relations between frequencies. I've selected 220 Hz as my fundamental frequency, and my next overtone will be an octave higher, the fundamental frequency times 2. That's 440 Hz. The next overtone will be a fifth higher than the second overtone, or an octave and a fifth higher than the fundamental. The fourth one will be 2 octaves higher than the fundamental, and a perfect fourth higher than the previous overtone. And as you can see, as I go up the overtones, the interval with the previous overtones gets smaller and smaller and smaller. As I go up, it reaches microtone. The recipe for making a classic saw oscillator is having each overtone's amplitude divided by its harmonic count. So for instance, the first overtone would be on maximum volume, the second one would be half the volume, third one would be third the volume, you can see it here also, and so on. So theoretically a saw wave should have infinite overtones. That's it for this lesson. I hope you got a little bit wiser. If you want to download this device and explore the world of harmonic sound, or generally learn about synthesizers and how to make great sounds, just visit our website www.synthschool.com.